Okay, before we dive deep into the world of salts, I want to give you a really powerful tool right from the start. Go ahead and scan this QR code or just visit MCQ Seriously, it's loaded with thousands of SPM questions. The best way to lock in this knowledge is through active practice, so definitely make it your new best friend.
Welcome, everyone. Today, we are tackling a topic that, let's be honest, trips up a lot of students in SPM chemistry, salts. But trust me, by the end of this, you're going to have the confidence to face any salt question they throw at you. So let's get right into it.
You know that feeling, right? You see a question about some weird precipitate or crystal shapes or confusing color changes, and your mind just goes blank. You are definitely not alone. These questions seem tricky, but here's the secret. They all follow patterns. And today, we're going to crack that code together.
So, where do we even begin? Well, we've got to start with the absolute foundation, the structure of a salt crystal itself. If you can get this, I promise, everything else about salts is going to click right into place. Just take a look at this. Every single salt crystal, whether it's microscopic or big enough to see, plays by these exact same rules. We're talking flat surfaces, straight sides, and fixed angles between them. It is not random at all. This perfect geometry happens because the ions inside are stacked together in an incredibly neat and orderly way. That's why a tiny grain of salt has the same basic shape as a huge crystal. The best way to think about it is like building with Legos. Each little ion just snaps perfectly into place next to the others, creating this super strong, organized, repeating pattern. That's the real secret behind all those beautiful, predictable shapes we see. Okay, so we get the outside structure. But now for the fun part. How do we figure out what's on the inside? This is where you get to become a chemical detective. We're going to look for clues to identify our mystery ions, our, chemical suspects.
So imagine this. I hand you a test tube with a totally unknown salt solution. Your mission is to figure out the positive ion, the cation, that's floating around in there. Our main detective tool for this job? A reagent. We add it in, we watch very closely, and we look for our first big clue, the formation of a solid, what we call a precipitate. Now, this clue sheet shows you exactly how it works. Let's say we add some sodium hydroxide. Both magnesium and zinc ions will give us a white precipitate, so at first glance they look identical. How in the world do we tell them apart? The trick is the next step. We add excess reagent, and look what happens. The zinc precipitate dissolves, it vanishes, but the magnesium one, it stays solid. That right there is our game-changing clue. And hey, listen up, because this is a classic exam trap. So many students see a white precipitate and they just jump to a conclusion. You have to do the extra step. You have to check if it dissolves in excess. A white precipitate with NaOH that does not dissolve. That's your smoking gun for magnesium ions. Do not forget that. All right, so this stuff is great for passing your exam, but you might be wondering, why does any of this matter in the real world? Well, it turns out salts are absolutely everywhere, and they play these huge, crucial roles in our everyday lives. Let's take a look. Just look at this list. Sodium chloride, that's just table salt. Sodium bicarbonate, that's the baking soda that makes your cakes fluffy. Calcium sulfate is the plaster of Paris they used to set broken bones in the hospital. And ammonium nitrate is a super important fertilizer that helps grow the food we eat. Salts are literally fundamental to modern life. And it's not just about industry and baking. It's about our health. We've all heard that too much salt is bad for you, right? Well, this is why. The most common salt in our diet, sodium chloride, is directly linked by doctors to high blood pressure. So understanding this chemistry is also about understanding our own bodies. All right, theory is one thing. Now for the most important part. Let's apply all this knowledge to some real SPM questions. This is how you're going to learn to spot the patterns and just breeze through these problems on exam day. Here we go, a classic from a past paper. The question is all about the famous brown ring test. This test is a dead giveaway for one specific anion. And the question is simple. What ingredients do you need to make this brown ring appear? Honestly, the best way to remember this is to think of it like a recipe. Step 1, add iron 2 sulfate and some dilute sulfuric acid. Step 2, tilt that test tube. And step 3, this is the most critical part. Very, very carefully pour concentrated sulfuric acid down the side. You'll get 2 layers, and that beautiful brown ring forms right where they meet. So here's the bottom line, the big takeaway.
When you see the words brown ring test, your brain needs to immediately scream nitrate ion. This is one of those things you just have to burn into your memory for the exam. Know the recipe, know the steps, and you will nail this question every single time.
Let's tackle another super common type of question. This one's all about electrical conductivity. Why can molten magnesium oxide conduct electricity, but the solid form can't? And how is that different from just plain old magnesium metal? This question really tests if you get the fundamental concepts. This slide just lays it out perfectly. In a pure metal like magnesium, you've got this sea of free-moving electrons that can carry a current no matter what. But, and this is a big but, in an ionic compound like magnesium oxide, the things that carry the charge are the ions themselves. When it's solid, those ions are locked up tight. But when you melt it, the ions are free to move around, and that's what lets it conduct electricity. Please, please remember this. It's a massive misconception that so many students fall for. For metals, it's those delocalized electrons doing the work. For molten or dissolved ionic compounds, it is always the freely moving ions. Get that straight, and you'll avoid a very common trap. All right, chemical detectives, we have one last case to solve. We've got this mystery solution, X. We get 2 clues. Clue number 1, add sodium carbonate, and a green precipitate appears. Clue number 2, add potassium sulfate, and you get a blue solution. So, what is our suspect? Let's break down the evidence here. A green precipitate with carbonate. That's the signature color of copper-2 carbonate. And a blue solution? Well, that is the classic color of aqueous copper-2 ions, like you'd get when you form copper-2 sulfate. You see? Both clues are pointing directly at the same culprit. And there you have it. Case closed. Both tests totally confirm the presence of copper-2 ions. That means our original mystery solution had to be a soluble copper-2 salt, something like copper-2 chloride. The colors gave it away. So let's wrap this all up. What are the absolute must-knows? 1, crystals are orderly and geometric. 2, treat ion tests like detective work. Look for clues in precipitates and colors. 3, remember that salts are vital in the real world. And 4, most importantly, practice, practice, practice is how you learn to spot these patterns instantly. You now have the complete toolkit to tackle pretty much any salt question they can throw at you. The real key now is to keep using these concepts. So what are you waiting for? Head over to mcqpm.com and put your new detective skills to the test. Which mystery are you going to solve first?